Question number 5, 2016, and the question is, in the first row, high spin transition metal complexes having the formula MH2O6Cl2 with D5 and D7 metal ions, the DD transitions are option A, spin forbidden for both, option B, spin allowed for both, option C, spin forbidden for D5 and spin allowed for D7, and option D, spin allowed for D5 and spin forbidden for D7. You have to choose the correct answer among these four options. So here one octahedral first row transition metal complex is given having the formula MH2O6Cl2, and the metal, two different metal ions are there, D5 and D7, so two different systems. Now you have to think about DD transition in those complex system. Now coming to the answer. So the complex in the question is MH2O6 Cl2. This is an octahedral complex, and the D systems in the question is D5 is chromium and D7 is cobalt. So the corresponding complexes are CrH2O6 Cl2 and COH2O6 Cl2. We know in the octahedral geometry, the d orbitals of transition metal will be splitted in two different sets of orbital. This is T2G and this is EG. The T2G set is comprising of dxy, dyz and dxz orbital, and the EG set is comprising of dx square minus y square and dz square orbital. This is happened because of the crystal splitting. The valence electrons of the transition metals will go into the d orbital. So now there will be a energy difference between the d orbitals. One set, there is a T2G set having lower energy and the EG set will be high energy. Thus, there is a chance of electronic transition from T2G to EG, which is called the DD transition. And because of this transition, emission of energy will happen and they will show color. That is why most of the time transition metal complexes are colored. Now, hypothetically, we can think about all kind of DD transition, but to give color, there has to be some selection rules. The first selection rule is spin selection, and the latter is spin orbit selection. First, we have to think about spin. So what is spin selection rule? It is first one, delta S. First one, delta S has to be 0 for spin allowed transition, and second one, delta S not equals to 0 for spin forbidden transition. We can show it by giving one example. Just think about two different sets of orbital, x1 and x2, and now think each of the sets of orbital having one electron. So the total spin of this configuration will be half plus half, that is 1. Now we can think that the electron from x1 will go to x2. The configuration will become here. You can see that the x1 become empty and x2 having pair of electron. Now the spin of this configuration is half minus half, that is 0. So delta S equals to S1 minus S2, that is 1 minus 0 equals to 1, that is not equals to 0. So this transition is spin forbidden. Another example for spin allowed transition. Think this is the configuration for two different sets of orbital A1 and A2. Let's think the configuration is like this: A1 having 3 electrons and A2 having 1 electron. The total spin of this configuration will be 3 into half minus half, that is 3 by 2 minus half is 1. Now let's think that the electron from the pair in A2 will break and it will move to A2 to make another pair. Now the configuration will be A1 has now single electron in each of this orbital, and A2 has a pair of electron in one of the orbital. Now the spin of this configuration will be the changed configuration S2, 3 positive half electron and 1 negative half electron. So again 3 by 2 minus half, this one. Now the delta S in this case is S1 minus S2, 1 minus 1, 0. So this transition is spin allowed. So you can easily understand when it will be spin allowed and when it will be spin forbidden. Now we have to think about our question D5 and D7 systems, the octahedral systems. Now for D5, the electronic for high spin D5 system, high spin, this is the configuration. Now let's see, it's one of the transition from T to G to EG. The configuration will look like one of the orbital of T2G is now empty and one of the orbital in EG having pair of electron now. Okay, so this is two different configuration after the DD transition from T2G to EG. Now the spin of the first transition S1 will be 5 into half, that is 5 by 2. The spin of the another configuration after the DD transition S2 will be 4 positive half electron and 1 negative half electron. So this is 4 by 2 minus half, that is 2 minus half, that is 3 by 2. Now the delta S equals to S1 minus S2, 5 by 2 minus 3 by 2, and this value will give 1, that is not equals to 0. So this transition in D5 octahedral system of MH2 6Cl2, the transition from T2G to EG electronic transition is spin forbidden. Now come to the D7 case. The configuration of D7 will be two pair of electrons in two orbitals of T2G and EG said singly occupied orbiting. Now think this transition happening between T2G and EG. The configuration will look like now. The T2G in the T2G said two orbitals having single electron and one having pair electron, and in EG set one having single electron and other having pair of electron. So two different configuration is possible after this DT transition. In first case S1, the spin of this configuration is how many positive half electron? 5, and how many negative half electrons? 2. So the value is 5 by 2 minus 1, that is 3 by 2. Here S2 value is again how many positive half electron? 5 into half, and how many negative half electron? 2. So 5 by 2 minus 1, 3 by 2. So the delta S equals to S1 minus S2, 3 by 2 minus 3 by 2, 0. So this transition is spin allowed transition, since the delta S value in D7 octahedral system of MH2O6Cl2, the electron transition from T2G to EG having delta S value is 0. Thus you got your answer. In case of D5 it is spin forbidden, and in case of D7 it is spin allowed. Thus this is your option, and which is your correct answer? C, spin forbidden for D5 and spin allowed for D7. So answer is C. For reference, you can look into the lecture on DD transition, that is lecture 22 by Professor Devashish Ray, Department of Chemistry, IIT Kharagpur, and this is the YouTube link. Thank you very much.